The next stoichiometry calculation we're going to look at are the mass to moles examples. So remember, we're talking about a situation where we're going to be given the amount of one chemical and we're trying to solve for the amount of another chemical. In this situation, they're going to tell us the mass of a particular chemical and want us to solve for the moles of something else. So now if we realize this, we really have again, another type of a two-step calculation. The second step is the first calculation that we did, the moles to moles. Well, now what we have is kind of a step before that. So we're given the mass of the chemical. Well, before we can go to the moles of the other chemical, we first need to change the mass of that chemical into its moles. Well, how do we change any chemical into its moles? We have to use a conversion factor. So the first step is going to be taking the mass of that chemical and multiplying by its molar mass conversion factor, or actually dividing by it to get to moles. So that's what our first step will be. So on page 309, they have sample problem D. So we're going to look at that one here. So in the question, they say the first step in manufacturing nitric acid is the oxidation of ammonia. So you can see the reaction there. Now you got to be careful. It does say it's unbalanced. What I have up here is actually the balanced reaction. So just real quick here, in terms of moles, the ratio of those four chemicals in mole amounts is 4 to 5 to 4 to 6. So a couple things we can see real quick here. Well, however much ammonia you have, I'm going to make that exact amount of nitrogen monoxide, NO, in terms of moles. However much ammonia I use, I'm going to get 3/2 the amount, 3 to 2 ratio, 6 to 4, however you want to say it, that amount of water produced. Okay. So in part A, the reaction is run using 824 grams of ammonia. So that's what we're given, 824 grams of ammonia, and they say excess oxygen. So what that's telling us is we've got an unlimited supply. It's not going to affect our calculation. And they want to know in part A how many moles of NO are formed. So they want to know moles of NO and then moles of water. So actually we're going to solve both problems at the same time. Oops, sorry, 824, not 8.24. The very first step, we're going to go from mass of ammonia to moles of ammonia. Well, it's the same step for both calculations. Okay? It's going to get us moles. Now we've got to go from moles to mass. So you can see in that sample problem there, they are putting both A and B right next to each other. They've got the mass of ammonia multiplied by its molar mass factor. Again, we're actually dividing. And then multiplied by the mole ratio conversion factor. So you can see then in the bottom of that sample problem, they actually plug in the numbers and say, okay, grams of ammonia multiplied by 1 over molar mass gives me the moles. And then I multiply by the mole ratios, the proportions, the conversion factor, to get the moles of the chemical that they're asking for. In this case, NO and water. All right, so what we'll do is I'm going to look at the first practice problem, in which they're talking about a reaction involving mercury. Again, you've got to be able to read the reaction and pull out, read the question to pull out the reaction. Oxygen was discovered when mercury 2 oxide was heated to decompose to form its elements. So, mercury oxide was decomposed to form its elements. There's our reaction. So, in the practice problem, how many moles of mercury 2 oxide are needed to produce 125 grams of oxygen? So if I want to make 125 grams, how many moles do I need? So we're given the mass of oxygen, and we're trying to find moles of mercury 2 oxide. So we start out with what we're given, 125 grams of the chemical O2. First step, we have to change to moles of oxygen. How do we get to moles of oxygen? Well, in 1 mole of oxygen, we have the molar mass of oxygen. So if we use 15.999 times 2, so we'll say 31.998 grams of oxygen. Grams cancel. Now we need to go from moles of oxygen to moles of mercury oxide. How do we go from moles of one thing to moles of the other? B over A. B's coefficient over A's coefficient. So for every 2 moles of mercury oxide, there will be 1 mole of oxygen. Now, so what are we saying here? We're in a 2-to-1 ratio. However many moles of oxygen we want to have, okay, however many moles of oxygen we want to have, we're going to have to introduce twice as many moles of mercury oxide. So 125 grams times 31, or multiplied by 1 over 31.998 times 2 moles. Significant figures here, we got 3. So again, depending on our molar mass and what periodic table we use, we would get 7.81 moles of HgO. All right, part B. You need to show me your work for how you solve for part B. In part B, they just want you to find how many moles of mercury would be made given that situation. Okay. All right. Okay, so we're good on that example. The last one that we're going to do is we're going to look at the mass-to-mass calculation. Now, think, oh my gosh, this is the last one, this is the hardest one. It's not new. What we actually have is a combination of the first 3 put together. So we'll be given the mass of a chemical, and we'll be asked to solve for the mass of the other chemical. So if we kind of look at this closely, moles to moles. That's the first calculation we learned how to do. We use B over A, multiplied by B over A. The second calculation we learned how to do was moles to mass. What did we have to use there? Molar mass of B. The third calculation we learned how to use, we learned how to do, was mass to moles. What did we use there? The molar mass of A. So if you look back at the very first screen where we talked about the number of calculations, this involves 3 steps. But it doesn't involve anything new, it just incorporates all 3 calculations into one big example. So on page 310, they have one involving tin fluoride. So you can see the reaction there. And they're asking how many grams of tin fluoride will be produced when we introduce 30 grams of HF. So if we introduce 30 grams of HF, how many grams of tin fluoride will be produced? Now you got to remember here, the coefficient, somebody might say, oh, it's going to be half as much because it's a 1-to-2 ratio. No, that's only true if we're talking about moles. Okay, we can't make that comparison with masses. So we're going to start out with 30 grams of HF, and we're going to try to solve for mass of SNF2. So you can see the example that they have set up there on the very bottom of page 310. They show there grams of HF multiplied by the molar mass conversion factor, multiplied by the mole ratio conversion factor, and finally multiplied by the molar mass conversion factor of SNF2. We've got to add molar masses. Remember, think about molar masses here. We don't include the coefficient if we're doing molar masses. It's just HF. So you can see what they're doing there in that calculation, how they're solving for that one. So what we're going to do here is we're going to look at the first practice problem. This will be, like I said, our last example. So in that first practice problem, there's a reaction involving nitrogen and oxygen and hydrogen. And they're asking how many grams of NH4NO3 are required to produce 33 grams of N2O. So you can see here, this is our setup. This is what we're given. and that's what they want us to solve for. Now, here can be something good to think about. Think about just in your head sort of what the steps would be. I need to go from mass of N2O to mass of NH4NO3. Now, I can't do that in one step. So what do I need to do? I need to first go to moles of N2O. Then for moles of N2O, I need to go to moles of NH4NO3. Then finally, I can go to mass. How do I go from mass of N2O to moles of N2O? I need to use the molar mass of N2O. How do I go from moles to moles? B over A, coefficients. How do I go from moles to mass of NH4NO3? The molar mass of NH4NO3. So this is good to do every time you do a problem, at least in your head. Say, okay, here's where I'm starting. These are the steps I need to do. Here's where I need to go. So let's actually set that one up. So we've got 33 grams of N2O times in 1 mole of N2O. We're going to have the molar mass of N2O. We can look that up here in a little bit. And then we're going to go from moles of N2O to moles of NH4NO3. We double check there. We got the reaction balanced, so that's good. When we want to get rid of moles of N2O, we want to go to moles of NH4NO3. And then the last step, we want to go from moles of NH4NO3 to mass of NH4NO3. So molar mass, you got to add up N2O. So here we'll do some whole numbers here. We'll just add up our whole numbers. So for N2O, 2 nitrogens and oxygen, we'll just call that 44.0. And then NH4NO3, so we'd have our 44 plus 2 more oxygens plus 4 hydrogens. We'd have a molar mass, we'll just call it 80.0. So 33 grams divided by 44 times 80, and we're going to get a final answer of 60 grams of NH4NO3. In this last example then, part B, they want you to find how many grams of water are produced. So what I want you to do there is solve for the amount of water that would be produced and be able to show me in class the work that you did for that one. All right, very last thing. This is just something to think about. As we solve all these problems, it's more of a strategy thing. Okay? This is going to be our strategery lesson. First thing you want to do, at least in your head, think about the type of problem. Then, number 2, think about the steps that you're going to need to solve it. All right, this is what I'm starting with. I first got to go to this, then that. Well, then what do I need to use? What conversion factors will I need to use? So you're just thinking, oh, I got to use molar mass there. I got to use mole ratio here. And at least it's giving you a plan to solve for the problem. Then you actually do the calculation. Okay, you show the actual calculation. You do the work. You label your numbers. Don't just pick up your calculator and start punching buttons. Okay? Because you're going to have too many things that you're going to have to memorize to know, oh, multiply here, divide there, this and that. Goes back to my classic phrase of the math and chemistry, it's easy. All we do is add, subtract, multiply, and divide. But you've got to know when to multiply and not divide, and so forth. Okay? So we've looked at our 4 different examples. Then we're going to do a ton of these in class. Obviously, our labs will be tied to this. So we're going to make chemicals and we're going to measure chemicals. Right? So you guys will get pretty good at this as we continue to work through the chapter.